Alright, hello. Today let's look at irrational numbers and surds, exercise 3A. Irrational numbers and surds. So to start us off, we're first going to look at the real number system. So they're the numbers that we're used to dealing with on a daily basis, whether it's whole numbers, decimals, fractions, positive or negative numbers. The numbers that we work with every day, they're part of our real number system. And within the real number system, we have names or ways of classifying the different types of numbers. So for example, whole numbers, we call them integers, whether it's positive or negative. So integers are our whole counting numbers. For example, they could be -2, -10, -507, -1. 0 is also an integer. 1, 2, 3, etc. So whole numbers, we call them integers. The next type of numbers that we have inside our real number system is rational numbers. So essentially, a rational number is any number that can be written as a simplified fraction. So any number that can be written as a simplified fraction. So, for example, 2/5, 2/5, it's a fraction. It's simplified. It is a rational number. A whole number, -3, it's a whole number, but technically it can be written as a fraction if you just put it over 1. So -3 is a rational number. For example, even decimals, 0.6, that is a rational number because we can write it as 3/5. It's a simplified fraction. And even recurring decimals like 0.3333333 forever, that's actually written as 1/3. So that 0.3 recurring is also a rational number. So whole numbers, fractions, or even decimals, they can be written as fractions, so they are all rational numbers. In particular, 0.6, we call it a terminating decimal because it's a decimal that stops. 0.6, stop, that's it. Versus 0.3, forever recurring, is called a recurring decimal. So we have inside our real number system integers, which are whole counting numbers. We have rational numbers, anything that can be written as a fraction. And we also have the family of irrational, irrational numbers. Essentially, anything not rational is an irrational number. So these irrational numbers are numbers which we cannot write as simplified fractions. Typically, these are our non-terminating and non-recurring decimals. So some classic examples of irrational numbers is √2. If you put it in a calculator, it's a decimal that never ends. Another classical example is our buddy pi relating to circles. So if you look at the grand scheme of things, look at the whole real numbers as our universe, pen, so that's, we look at all the real numbers. Inside the real numbers, we can either be a rational or irrational number. It's one or the other, you can't be both. And inside the rationals, we have the family of integers. And that's essentially our real number system in a nutshell. So moving on, we're going to look at surds. We've seen these before in year 9. Surds are pretty much anything that we can write with a square root symbol. So square root of 2 is a surd. 5 root 11 is a surd. It has square root of 11 in it. 1 plus root 5 is also a surd. It has a square root of 5 in it. Is root 4 a surd? Well, can we simplify root 4? Yes, square root of 4 is 2. So square root of 4 is not a surd. What about cube root of 8? Can we simplify that? Well, it has a square root sign, but doesn't mean it's necessarily a surd, because cube root of 8 is a 2. That's a whole number, so that is not a surd. There are some properties of surds. For example, if you're square rooting the product of two numbers, then you can break it apart as the product of the individual square roots, or the surds. Similarly, if you're trying to divide, then the square root of x over y, you can break it apart, square root of x over square root of y. Now, when we're doing some questions, if the question is asking you to simplify your surd, then all it's trying to say is, well, the first starter thing you have to do is, can you write the surd you've got as a perfect square multiplied by some number? Now remember, perfect squares, these are 1 squared, which is 1, 2 squared, which is 4, 3 squared, which is 9, 16, 25, etc. So let's do some examples. Example 1. We have to classify, are the following numbers rational or irrational numbers? So part A, is negative root 3 rational or irrational? Well, can you write root 3 as a simplified fraction? No. Essentially, all surds are irrational numbers. Root 3 is a surd, so negative root 3 is irrational. Might make a note back here that all surds are irrational numbers. Let's do part B. Is 137% rational or irrational? Well, can we write 137% as a simplified fraction? Per set means part of 100, so 137% is 137 over 100. Oh, look, it's a fraction. It's a simplified fraction. So 137% is a rational number. C, 3/7. That's straightforward. It's a fraction. It's simplified. It is, of course, a rational number. Example 2. We are going to simplify some surds. Let's first simplify square root of 32. So, as we said before, simplifying means, can we break 32 apart into a product of a perfect square and something that's not perfect square? 32 is 16 lots of 2, or 2 lots of 16. So we can use the multiplying pattern. So the square root of the product of two things is the product of the individual square roots. Square root of 16 is 4, so it becomes 4 root 2. And you'll note that in the simplified fraction, we don't have any products or multiplying signs between the 4 and the square root. So it's a ninja time sign, it just disappears. Part B, let's do another one. Let's simplify 3 root 200. So what we do here is, first leave the coefficient of 3 alone. Just copy and paste it, leave it alone, we'll deal with it later. Can we simplify root 200? So can we write 200 as a product of a perfect square and some other number? 100 is a perfect square, 100 times 2. So that becomes 3 lots of 100, 3 lots of square root of 100, lots of square root of 2. Square root of 100 is 10. So 3 times 10 times root 2. 3 times 10 gives me 30. So it becomes 30 root 2 as my simplified surd. Let's do another one. C, 5 root 40 over 6. Leave the coefficients alone. So leave the 5 and 6 alone. Let's deal with the surd. Can we write square root of 40 as a product of a perfect square and something else? 4 and 10 gives me 40. So then let's apply the surd product pattern. So it becomes root 4 times root 10. So that's 5 lots of 2 lots of root 10 over 6. So 5 times 2 gives me 10. So that's 10 root 10 over 6. We can keep simplifying. So 10 and 6, looking at the coefficients, we can simplify that. If I divide both of them by 2, so 10 divided by 2 gives me 5, 6 divided by 2 gives me 3. So I get 5 root 10 over 3. When I'm simplifying the surds, we only simplify the coefficients, so the numbers in front. You don't try and halve root 10. You don't make that a root 5. You just do it with the coefficients. Let's do D. It is root 75 over 9. So you're square rooting a fraction, so we can split it. So that becomes square root of 75 over square root of 9. 75 is a pretty big number. Can we write it as a product of a perfect square and some other number? Yes. Obviously, 75 is 3 lots of 25, and square root of 9 is 3. Let's break the top apart to be square root of 25 over times root 3 or over 3. So that becomes 5 root 3 over 3. Look at your coefficients, 5 and 3. I can't cancel it any further, so I'll just leave it alone as 5 root 3 over 3. So that's simplifying surds. Can you split them up into a perfect square and some other number, and then make it nice and pretty so that the surd is nice and small. Example 3, which I do now, is working on backwards. So example 2 was looking at, here I have a square root of a pretty big number. Let's simplify down, making it nice and small. Going back the other way, given a nice simple surd, can we say what was the original square root that we're looking at? So example 3, express the following as square root of a positive integer. So one whole number, integer. So how can we write 2 root 5 as square root of one single number? Well, working backwards, we're looking at our coefficient first. So we've got a coefficient of 2. Well, square root of what gives me a 2? Well, square root of 4 gives me a 2. So the 2 can be replaced with square root of 4. And then you multiply that by square root of 5. So reversing the pattern we were using before, we can smush them together. So that's the square root of 4 times 5. So it's the square root of 20. Let's do another one. 7 root 2. So you're thinking, what square rooted gives me 7? Well, square root of 49 gives me 7. And I'm multiplying by the root 2 there. Reversing it, it becomes square root of 49 times 2. 49 times 2 gives me 98. So working backwards of 7 root 2, we can rewrite that as square root of 98 as one whole square root of one whole integer. And that's essentially how to simplify surds. So the relevant exercises to do: exercise 3A, page 169. Simple familiar questions. We have question 3A, D, E, G. Question 4, B, D, E, G. Question 5, B, D, F, G, J, and L. Question 6, C, D, G, J, L, N, P, and S. Question 7, B, F, H, K, and L. Question 8, B, D, G, K. Question 9, B and C. Question 10, B and C. Question 11, B and C. Question 12, B and C. And to finish it off on a lovely complex familiar question, question 13. And that's it. I'll see you next time.